Good morning, dear students. Welcome back to physics class. In today's class, the discussing topics are A. Deviation of real gases from ideal gas. B. Deduction of Boyle's law and Charles law from perfect gas equation. And C. Kinetic interpretation of pressure and temperature. In today's class, let us study about how can show the deviation of real gases from ideal gas behavior graphically. You know, real gases approach the ideal gas behavior for low pressures and high temperatures. And also you know that ideal gas equation PV is equal to nu RT. For 1 mole of ideal gas, nu is equal to 1, then PV is equal to RT. So, PV by RT is equal to constant. When we draw a graph by taking pressure P along x-axis and PV by T along y-axis, we will get a straight line which is parallel to x-axis for ideal gas. This means that it has constant value at all temperature and pressure. But in case of real gases, graph approach ideal gas behavior at a high temperature and at low pressure. At a high temperature and low pressure, molecules are far apart. When temperature is increased, the molecules will move randomly far from each other. As a result, molecular interaction decreases, the gas behaves as an ideal gas. This ideal behavior comes into picture when the molecules present inside the gas cannot interact with each other. Now, you can see how can deduce Boyle's law and Charles law from perfect gas equation. You know Boyle's law. According to Boyle's law, at a constant temperature, pressure of given mass of gas varies inversely with volume. Here, we have to derive Boyle's law from perfect gas equation, which is PV is equal to nu RT. By considering the temperature T and nu, which is number of moles present in the given gas, constant. Therefore, the expression becomes as PV is equal to constant, which is the mathematical form of Boyle's law. The given graph shows the experimental pressure volume curves, which are represented by solid lines for steam at 3 different temperatures T1, T2 and T3, where T1 is greater than T2, which is greater than T3, which are to be compared with Boyle's law, which is represented by dot lines. That is, by using this graph, we can compare the experimental PV curves with the theoretical curves predicted by Boyle's law. Here, P is measured in units of 22 atmosphere and V is measured in units of 0.09 liters. You should mean the experimental curves are represented by solid lines and theoretical curves are represented by dotted lines. From this graph, you can see that at high temperature and at low pressure, the experimental curve is come closely to the theoretical curve. I told earlier, at high temperature and at low pressure, the real gas whose behavior come close to the ideal gas behavior. We have considered the real gas is steam. Similarly, let us derive Charles' law from the ideal gas equation. You know the Charles' law. According to Charles' law, for a fixed pressure or a constant pressure, volume of given mass of a gas is directly proportional to its absolute temperature. Consider if pressure P is constant, then from the ideal gas equation, PV is equal to nu RT, V by T is equal to nu R by P, which is equal to a constant. Therefore, V by T is equal to a constant. It is the mathematical form of Charles' law which was deduced from the ideal gas equation. The figure shows the experimental TV curves which are represented by solid lines for the real gas carbon dioxide gas at three pressures P1, P2 and P3, where P1 is greater than P2, which is greater than P3, compared with the theoretical curves which is suggested by Charles' law represented by dot lines, where T is measured in units of 300 Kelvin and V is measured in units of 0.13 liters. From these all points, you should conclude that an ideal gas agrees with both Boyle's laws and Charles' law. It is very important to remember that an ideal gas is not existed practically. It is a theoretical concept, but its knowledge is very essential to study about the nature of a real gas. There is one important law connecting to the nature of an ideal gas, which is Dalton's law of partial pressure. According to Dalton's law of partial pressure, the total pressure of a mixture of ideal gases is the sum of partial pressures. Consider if there are several ideal gases mixed together in a vessel, then the total pressure of that vessel is equal to sum of partial pressures. What is partial pressure? It is the pressure exerted by a particular gas if only that gas is present in that vessel. For example, consider if in a vessel there is a mixture of three gases named as A, B and C. So, the partial pressure of A is equal to pressure exerted only by A, and considering B and C are not present. Similarly, partial pressure of B is equal to the pressure exerted only by B, and considering A and C are not there, and similarly for C also. Then total pressure P is equal to P1 plus P2 plus P3, where P1 be partial pressure of gas A, P2 be the partial pressure of gas B, and P3 be the partial pressure of the gas C. Here, by applying Dalton's law, the total pressure of mixture of these gases A, B and C is sum of the partial pressure of A, the partial pressure of B and the partial pressure of C. It is important to see that the Dalton's law of partial pressures is in agreement with ideal gas law. To show how perfect gas equation concludes Dalton's law of partial pressures. Suppose we have taken a mixture of ideal gases in a vessel. These gases do not interact with each other. By perfect gas equation, which is PV is equal to nu RT, where V be the volume of the gas, P be the pressure exerted by the gas, T be the temperature, and nu be the number of moles of the gas. As they are mixture of ideal gases, then total number of moles nu is equal to nu1 plus nu2 plus etc. Then the ideal gas equation takes in the form of PV is equal to nu1 plus nu2 plus etc. into RT. So P is equal to nu1 plus nu2 plus etc. into RT by V, which is the sum of nu1 RT by V, nu2 RT by V, etc. So P is the sum of P1, P2, P3, etc., where P1 be the partial pressure of the gas 1, P2 be the partial pressure of the gas 2, and so on. Therefore, total pressure due to the mixture of gases is equal to the sum of the partial pressures of the gases. In previous section, you learned about kinetic theory and important assumptions related to the kinetic theory of common gases. Now, what is kinetic theory of an ideal gas? You know that molecules of gas are in the continuation of motion without any stoppage. So, they are in incessant random motion. They are colliding against one another and with the walls of the container. All collisions are elastic in nature. That is, in the elastic collision, total kinetic energy and momentum before collision is equal to the total kinetic energy and momentum after collision. So, we can say that in the elastic collision, total kinetic energy and momentum are always conserved. What does kinetic theory of gas tell? At ordinary temperature and pressure, the molecular size is very small as compared to the intermolecular distance between them. In case of gas, molecules are very far from each other and the size of molecules is small as compared to the distance between them. As a result, the interaction between them is negligible. As there is no interaction between the molecules, there will be no force between the molecules. As a result, molecules are moving freely as per Newton's first law of motion. These molecules should have a long straight line, but when they come closer, they experience the intermolecular forces. And as a result, their velocities will change. This phenomenon is known as collision. These collisions are always elastic in nature. As next topic, I am going to discuss on kinetic interpretation of pressure and temperature. First for kinetic interpretation of pressure. What is kinetic interpretation of pressure? It is the calculation of pressure of an ideal gas based on kinetic theory. Consider a gas enclosed in a cube of side L. Take the axes to be parallel to the sides of the cube as shown in figure. Also, we have considered only one molecule which going to hit with wall of the container and bounces back. Let the velocity of the molecule when it is moving be Vx, Vy and Vz. They are x component, y component and z component of velocity respectively. When the molecule bounces back, its velocity will be minus Vx, Vy and Vz. Since the collision is elastic, the molecule rebounds with the same velocity. Its y and z components of the velocity do not change in the collision, but x component of velocity reverses sign. Then what should be the change in momentum? It is equal to final momentum minus initial momentum. So, Pf minus Pi is equal to minus mvx minus mvx, which is equal to minus 2mvx, where Pf be the final momentum and Pi be the initial momentum. This change in momentum is imparted to the wall due to the collision. By the principle of conservation of momentum, the momentum imparted to the wall in the collision is equal to 2mvx. It is due to the one molecule. Then, our aim is to calculate the pressure exerted on the wall due to the number of molecules collided in the time delta t. As pressure is equal to force per unit area, so first we have to calculate the force. Since force is equal to change in momentum per unit time or rate of change of momentum, in accordance with Newton's second law of motion. You see that by calculating the rate of change of momentum of the number of molecules colliding against the wall in time interval delta t, we can find the pressure exerted on the wall. Earlier, we had calculated the momentum imparted to the wall in the collision due to only one molecule, which is 2mvx. In a small time interval delta t, a molecule with x component of velocity Vx will hit the wall if it is within the distance Vx delta t from the wall, as the distance traveled by the molecule in time interval delta t is equal to speed into time, which is Vx delta t. This shows that all molecules within the volume, which is a Vx delta t, only can hit the wall in the time delta t. Here, volume V is equal to area of side of the cube multiplied with the distance traveled by the gas in time interval delta t. But out of these molecules, half of these are moving towards the wall and other half away from the wall. Then, what should be the actual number of molecules with velocity Vx, Vy, Vz hitting the wall in time interval delta t? It will be equal to half of total number of molecules in the given volume V. It will be equal to 1 by 2 into A into Vx into delta t into n, where n be the number of molecules per unit volume. It is the number density of the gas molecules. Therefore, total number of molecules that hit the wall is equal to 1 by 2 into n into a Vx delta T. So, the total number of molecules that hit the wall is equal to 1 by 2 into n a Vx delta T. Then, total momentum imparted to the wall is equal to the momentum imparted to the wall due to single molecule multiplied by total number of molecules that hit the wall in time interval delta t, which is equal to 2mvx into 1 by 2 into n a vx delta t. After simplifying, we will get total momentum imparted to the wall is equal to an vx square delta t m. Now, force exerted on the wall is equal to rate of change of momentum, which is equal to change in momentum divided by time interval delta t, which is equal to an v square delta t m by delta t is equal to an v square m. Then pressure exerted on the wall P is equal to F by A is equal to N M V square. Therefore, P is equal to N M V square. This is true for group of molecules having with velocity Vx. You have to notice these points all. First one, all the molecules inside the gas will not have the same value of velocity. Second one, all will have different velocities. And third one, the above equation is valid only for pressure due to the group of molecules with speed Vx in x direction, and n stands for the number density of that group of molecules. Therefore, total pressure due to all such groups will be obtained by summing over the contribution due to all the molecules, which is P is equal to Nm average value of Vx square. We have pressure P is equal to Nm average value of V square. Suppose the gas is isotropic, it means that the velocity of all the molecules can be same in any direction. Therefore, average value of square of Vx is equal to average value of square of Vy is equal to average value of square of Vz. It should be equal to 1 by 3 into V square. Therefore, the pressure P is equal to 1 by 3 into N into M V square, where V square is equal to average value of squared speed. Let us see what is the justification of these assumptions. We have assumed the container containing the gas is a cube. Here, the shape of the container is not important because the factor A is not found in the final result or the expression for the pressure P. For a vessel of any arbitrary shape, we can choose a small infinitesimal or planar area and can prove the above derivation. We will see that A and delta T are not there in the final result. According to Pascal's law of transmission of pressure, pressure in one portion of gas in equilibrium is the same as anywhere else. We have the number of molecules hitting the wall in time interval delta t is equal to 1 by 2 into n into a into Vx delta t, which is with random collisions and a steady state of the gas. Thus, if a molecule with velocity Vx, Vy and Vz acquires a different velocity due to collision with some molecules, there will always be some other molecule with a different initial velocity, which after a collision acquires the same velocity, which is Vx, Vy, Vz of the previous one. Even if the molecular collisions are not too frequent and the time spent in collision is very small compared to the time between two successive collisions, it will not have any effect in the calculation for the pressure P. And then, what is kinetic interpretation of temperature? It states that the average kinetic energy of a molecule is directly proportional to the absolute temperature of the gas, which is independent of pressure, volume or nature of the ideal gas. We have pressure P is equal to 1 by 3 into Nm V square, where V square is the average value of squared speed. By multiplying with V on both sides of the expression, we get PV is equal to 1 by 3 into NV mV square. And also multiplied by 2 by 2, we get PV is equal to 2 by 2 into 1 by 3 into NVmV square, which is equal to 2 by 3 into Nm into 1 by 2 mV square. Since small letter n is equal to capital letter N by V, which is the number density of the gas molecule or the number of molecules per unit volume, then the expression will be PV is equal to 2 by 3 into N into 1 by 2 into mV square. Therefore, PV is equal to 2 by 3 into E, where E be the kinetic energy, which is E is equal to N into 1 by 2 into mV square. This is the basis of kinetic interpretation of temperature. So, we have the expression PV is equal to 2 by 3 into E, which is the expression 1. From ideal gas equation, PV is equal to nu RT, since nu is equal to N by Na and R is equal to Kb Na. Then it will become as PV is equal to N by Na into Kb into Na into T. So, it will get in the form of NkBT. So, PV is equal to NkBT, which is the expression 2. From the expressions 1 and 2, we get 2 by 3 E is equal to NkBT. So, E is equal to 3 by 2 into NkBT. Dividing E by N, we have E by N is equal to 3 by 2 into kBT. Since 3 by 2 into kB is the constant, so E by N is directly proportional to T, which is the absolute value of temperature. You know that E by N is the average kinetic energy, so it can say that average kinetic energy E by N is directly proportional to the absolute temperature. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.